Good morning. Myself, K. Ravi Kumar, Associate Professor, Department of Pharmaceutical Chemistry, School of Pharmacy, Alla Narasimha Reddy Education Society Group of Institutions, Hyderabad. So today we'll discuss about the effect of substituents on acidity of phenols. The objectives of today's class. At the end of the class, the students able to predict the effect of electron withdrawing groups on acidity of phenols. How the effect of electron withdrawing groups will be there on acidity of phenols, and how the effect of electron donating groups on aromatic nucleus will affect the acidity of phenols, and students will be able to predict the relative strength of different phenols, various phenols. They will identify the which is more acidic in nature and which is less acidic in nature. That will be done in the today's class. Coming to the acidity of phenol, we know that we have seen in the last class that phenols are more acidic in nature, having a pK value of approximately 10. Because phenols are more acidic in nature because the we have seen this aromatic nucleus is acting as electron withdrawing group. When it is acting as electron withdrawing group, the CH2 which is there, it is acting as having a sp2 hybridization. Because of that, it will try to pull the electron cloud from the oxygen. So there is a I minus effect takes place. I minus effect takes place. Because of that, this oxygen will have less electron negativity. Electron cloud on the oxygen decreases. When electron cloud on this oxygen decreases, it will try to impact on other atom which is attached to that. The other atom which is attached to that is hydrogen. So it will try to pull the electron cloud from hydrogen, so that the hydrogen will, the bond between oxygen and hydrogen becomes very weak. The hydrogen will go out. So why that is happening is because of electron withdrawing group effect of phenol, aromatic nucleus. So because of electron withdrawing group, that is aromatic nucleus, the electron cloud on the oxygen decreases. In turn, it will try to pull the electron cloud from weak atom, that is hydrogen, so that hydrogen goes out because of weak bond. So it forms a strong stable ion, that is phenoxide ion. We have studied in the last class that phenoxide ion is more stable than that of phenols. Why? Because phenoxide ion is having delocalized negative charge around the aromatic nucleus, whereas in phenols, the oxygen, when it is donating electrons to the aromatic nucleus, it forms a positive charge. So there is a positive charge on oxygen and negative charge on aromatic nucleus, that there is a repulsion and power potential energy increases. So when phenol and phenoxide ion, if you take, phenoxide ion is more stable than that of phenol. So we have seen the acidity of phenol, and the pK value of phenol is approximately 10. We know that more the pK value, the acidity decreases. The less the pK value, the acidity increases. So phenols are more acidic than that of alcohols, which is having a pK value of 16 to 18. Whereas phenols are less acidic than that of carboxylic acid, because carboxylic acid is having a pK value of 5. So phenols are having acidity. But what is the effect of substituents on phenols? What is the effect of substituents on phenols? Whether the acidity of phenols increases or acidity of the phenols decreases. So today's class we will discuss about the effect of substituents on substituents on acidity of phenols. So we know that there are two different types of substituents, that is electron donating groups and electron withdrawing groups. So substituents will have great effect on acidity of phenols. How? It may increase the acidity or it may decrease the acidity. Right? So two types of substituents. One is electron withdrawing groups which withdraws the electron cloud from the aromatic nucleus. So here if you see this EWG, which is electron withdrawing group, it will try to withdraw the electron cloud from the aromatic nucleus, which in turn will try to pull the electron cloud from oxygen means electron withdrawing group will have ability to pull the electron cloud from aromatic nucleus, in turn from oxygen. So availability of electron cloud on oxygen decreases. When availability of electron cloud on oxygen decreases, the oxygen will try to pull the electron cloud from weaker atom, that is hydrogen. So the bond between oxygen and hydrogen weakens, the hydrogen goes out of the oxygen, and the acidity increases. Means, in other terms, electron withdrawing group stabilizes the phenoxide ion, resulting in increase in the phenol acidity. So other type of groups which are there here are electron donating group. Electron donating group, what they do? Electron donating groups, they donate the electron cloud to the aromatic nucleus. Means electron cloud on the aromatic nucleus increases. When electron cloud on aromatic nucleus increases, that in turn increase electron cloud on oxygen. So oxygen is very stable. Oxygen is more electron rich. It will not have affinity to lose a proton, because electron oxygen is having more electron cloud, so it will not lose a proton. The acidity increases. Means, in other term, electron donating group destabilizes the phenoxide ion. Destabilizes phenoxide ion. Why? Because it is not going to lose the proton, so phenoxide ion is not formed effectively, so acidity decreases. Means electron withdrawing group increases the acidity, electron donating groups decreases the acidity. That point we have to remember. So what are the different electron withdrawing groups? Electron withdrawing group on aromatic nucleus strengthens the acidity of phenol. We have studied again. Electron withdrawing groups will increase the acidity. Why? Because it enables the ring to withdraw the more electrons from phenoxide ion. Why electron withdrawing group increase the electrons from phenoxy ion? Because electron, if you take the example of this nitrophenol, nitro group, we know that it is electron withdrawing group. Because of I minus effect, inductive minus effect, this nitro group will try to pull the electron cloud from aromatic nucleus. The aromatic nucleus will lose the electron cloud, which act as a withdrawing group, will try to pull the electron cloud from oxygen. So oxygen will try to donate the electron cloud to this aromatic nucleus. So it enables, the electron withdrawing group enables the withdrawing groups from oxygen, so reduces electron cloud from on oxygen. So when an oxygen electron cloud decreases, it stabilizes. It stabilizes the phenoxide ion. So it stabilizes. How it stabilizes phenoxide ion takes place? By the loss of proton. By the loss of proton, it stabilizes the phenoxide ion. When phenoxide ion is stabilized, then acidity increases. So electron withdrawing groups such as NO2, nitro group, chlorine group, any halogens, nitrile groups, carboxylic acid group, COOH, sulfonic acid group, any aldehyde groups, or ethers or esters, these are all acting as electron withdrawing groups. Withdrawing group we have studied already. What is that withdrawing group? Any atom which is having positive charge, any atom which is directly attached to aromatic nucleus bearing positive charge can act as electron withdrawing group. So here this nitrogen is having positive charge when it is because it is attached to oxygen. Oxygen is more electronegative than that of nitrogen. So any atom which is attached to aromatic nucleus bearing positive charge will act as electron withdrawing group. So nitro group or chlorine or CN or COOH or SO3H or aldehyde group or ketone group will try to increase the acidity. For example, if you take example of nitrophenol, acidity increases. Orthochlorophenol or parachlorophenol, acidity increases than that of phenol. If you take example of cyanophenol, acidity increases. So other functional groups, the nature of phenol, the nature of molecule changes. So here the point you have to remember is electron withdrawing group. will increase the acidity. How it increases acidity? It decreases it withdraws electron cloud from aromatic nucleus. Electron cloud and aromatic nucleus decreases. That in turn withdraws electron from oxygen. The oxygen becomes unstable. So it stabilizes. How it stabilizes? By the loss of proton. When proton is lost, it gains electron from proton. So stabilization takes place. So phenoxide ion is stabilized. So by the loss of proton, acidity increases. We'll take one example here. Para-nitrophenol is more acidic than phenol. Is it true? Phenol is having a pK value of 10. Para-nitrophenol is having a pK value of 7.2. So which is having less pK value? Para-nitrophenol or orthonitrophenol is having less pK value. The less pK value, more the acidity. So when you compare para-nitrophenol and the phenol, para-nitrophenol is having less pK value. Definitely phenol is less acidic than that of para-nitrophenol. So when para-nitrophenol, when it is treated with water, definitely the stability of para-nitrophenoxide is formed. The stable para-nitrophenoxide is formed very fastly than that of phenoxide ion. So the para-nitrophenoxide is more stable than that of simple phenoxide. Why? Because of electron withdrawing group. Because of electron withdrawing group. So when you take an example, phenol and phenoxide ion, which forms very fastly, para-nitrophenoxide is formed very fastly than that of phenoxide ion. That is the reason pK value of para-nitrophenol or orthonitrophenol is 7.2. If you see the mechanism involved here, if you see the resonance forms of para-nitrophenoxide ions, so we know that the pair of electrons which are there are delocalized into the nitro group. Means there are the conjugation, conjugation is more, the electron delocalization is entered into the nitrophenol, so the stability of phenoxide is more. That is the reason para-nitrophenoxide is more stable. If you see, we know that electron withdrawing nitro group is electron withdrawing group. It start pulling the electron cloud. See here, if you see here, we know that nitrogen is attached to two oxygens. Oxygens are electron negative. When they are pulling the electron cloud, pi bond is shifted to oxygen, it becomes O minus. When it is forming O minus, this will try to pull the electron cloud. So nitrogen become positive. It will try to pull the electron cloud from aromatic nucleus. So it will pull the electron cloud. When it is pulling the electron cloud, the pi bond shifts here and this become positive to nullify this positive charge. Then the pi bond shifts here. So oxygen will lose proton very effectively. Oxygen will lose proton very effectively and negative charge gains. So here, because of oxygen pair of electron is entering into the aromatic nucleus, in turn it is entering into the nitro group, the loss of proton is very, very fast and forms the stable phenoxide ion. Nitrophenoxide ion is very fast. So here what happens? Whenever para-nitrophenol is reacting with water, water abstracts the proton and form hydronium ion very fastly. The pair of electron which is there will undergo delocalization to form para-nitrophenoxide ion, and stable para-nitrophenoxide ion is formed, and the reaction will not be easy to form back para-nitrophenol. So para-nitrophenoxide is more stable and loses proton very fastly than that of para-nitrophenol. And you can compare here which is more stable. In para-nitrophenoxide ion, only it bears negative charge. See here there is a negative charge, and here negative charge, here negative charge, and oxygen negative charge. Whereas para-nitrophenol, oxygen will get positive charge and other aromatic nucleus will get negative charge, similar to that of phenol. Which is more stable? Para-nitrophenoxide is more stable than that of para-nitrophenol, and it is more acidic. By seeing the pK value, we can confirm that pK value of para-nitrophenol is 7.2 and pK value of phenol is 10. So the less the pK value, more the acidity. So effect of electron withdrawing group on acidity, that is increase the acidity. So you can see other other isomer of para-nitrophenol, it is metanitrophenol. If you take the metanitrophenol, acidity increases definitely, but the effectiveness of acidity compared to ortho and paranitro is decreased. So here, whatever the meta nitrophenol is there, it is not delocalizing the charge into the nitro group. So electrons are not shifting into the nitro group. The nitro group is not having affinity, effectiveness, but when you compare phenol and meta nitrophenol is more acidic in nature. Why? Because here there is a I minus effect takes place. I minus effect takes place. So nitrogen is trying to pull the electron cloud from aromatic nucleus by I minus effect. So R minus is not effective because electron cloud is not entering into the nitro group. So that is the reason when you compare paranitrophenol, the pK value is 7.2, whereas metanitrophenol, the pK value is 8.4, whereas phenol, it is 10. When you compare here, phenol is less acidic than that of metanitrophenol and paranitrophenol. Means here in metanitrophenol, the charge is not delocalized into the nitro group. Into the nitro group, it is not delocalized. Whereas in ortho and para, electrons are delocalized. Electrons are delocalized into the nitro group. So distribution takes place and stability increases. Stability increases. So if you take the other example for an electron withdrawing group, more the substituents electron withdrawing group on aromatic nucleus, the strength of the acid acidity of phenols increases. For example, if you take a 2,4 dinitrophenol, if you have one nitrophenol, the acidity came from 10 to 7.2. If you have two nitro groups at ortho and para, the strength of the acid increases, the pK value decreases to 4, means the acidity increases. And if you have three nitrophenols, means ortho, two ortho groups, you have nitro groups, and para also you have a nitro group, the strength of acid is increased drastically and pK value is 0.4. Very strong acidity, very strong acid. So when you compare phenol, nitrophenol, dinitrophenol and trinitrophenol is very strong acid with pK value 4.4, and dinitrophenol with a pK value of 4, and nitrophenol with a pK value of 7.4, 7.2, and the phenol it is 10. So the conclusion here is when the electron withdrawing group is present on the aromatic nucleus, acidity of phenol increases. Coming to the electron donating group, what is the effect of electron donating group on acidity? So what do electron donating group? The name indicates these electron donating group will try to donate the electron cloud to the aromatic nucleus. When electron cloud is increased, see here, we'll take the example of electron donating group. This electron donating group will try to donate the electron cloud to the aromatic nucleus. Electron cloud on aromatic nucleus increases. When electron cloud aromatic increases, this will increase the electron cloud on oxygen. Oxygen is more electron rich and it's stable. It is stable, so it will not lose electron. It will not lose the proton very fastly. So acidity decreases. If at all it loses the proton, the charge on the oxygen is destabilized. The charge on the oxygen destabilizes because there is a positive charge on this and positive and negative charge on this. So electron cloud on the aromatic nucleus and oxygen increases. Loss of proton will not take place very effectively. So it destabilizes. The destabilizes phenoxide ion. Destabilizes phenoxide ion. Then and prevent the loss of proton, decreases the acidity. So examples for electron donating groups such as any alkyl group, methyl, ethyl, propyl group, or methoxy group, propoxy group, aniline, amine group, NH2, or substituted amine groups. They are all electron donating groups which decreases the acidity of phenol. If you take toluene, if you take a methyl, orthomethyl phenol or paramethyl phenol, the acidity decreases. The acidity decreases. So electron withdrawing group, the acidity increases. Electron donating group, the acidity decreases. If you see here, we'll take the example paracrisol. Paracrisol, that is methyl group. Methyl group is electron donating group. It will try to donate the electron cloud. Electron cloud on this aromatic nucleus increases. So the electron cloud in turn, electron cloud on oxygen is more. So it will not have a tendency to lose proton very effectively. So it will lose protons slowly. That is the reason pK value of paracresol is 10.3, whereas phenol it is 10. So when you compare here, the acidity is slightly less than that of phenol, right? So why? Because it destabilizes the phenoxide ion. It is same as it of ortho position also. Ortho methyl group is forming a double bond here, and the negative charge increases, so it will not lose the proton very fastly. So orthocresol or paracresol will have pK value of 10.3, and it destabilizes the phenoxidine. Whereas metacresol, there is no effect of methyl group. Methyl group will not have effect on this delocalization, so it will not increase the electron cloud and aromatic nucleus uh, by R plus effect or hyperconjugation. It will it will produce by inductive effect. So the effect will be very less. So the acidity is more for metacresol than that of ortho or paracresol. So the point here we have to remember is electron withdrawing group increase the acidity, electron donating group decrease the acidity. We'll see the relative strength of various phenol substitute phenols here. Phenol is having a pK value of 10. Cresol, the methyl group which is there, methyl group, at orthocresol, the pK value increases, mean acidity decreases. So metacresol and phenol, they're almost similar, 10.1 and 10.0. And when you see the electron withdrawing group like chloro group, sorry, electron withdrawing group with chloro group, though it is, we know that chlorines are electron withdrawing group and orthopara directors. Here we need to talk about withdrawing group. So it will try to withdraw the electron cloud from the aromatic nucleus, so increase acidity. So compared to phenol, this is 8.6, 9.1 and 9.4. So ortho is pulling the electron cloud more than that of increased acidity. Orthochlorophenol is having more acidity than that of parachlorophenol and metachlorophenol. Whereas coming to methoxy group is an electron donating group. Electron donating group, it is approximately having same 10.3 or 10.2. Acidity decreases compared to the phenol. And nitrophenol, the acidity increases because it is electron withdrawing group. So it is 7.2 compared to the phenol 10. So parahydroxybenzaldehyde, the acidity is 7.6. But when you go for disubstitution or trisubstitution, the acidity drastically increases. Compared to phenol 10, the 2,4-dinitrophenol, it is 4, and the 3,5-dinitrophenol, it is 6.7. Though these are having same nitro group substitution, but the position is different. It is ortho position and para position. The delocalization is involved into the nitro group, whereas 3,5-dinitrophenol, the delocalization is not involved into the nitro group. So the acidity is decreased slightly. Acidity is decreased slightly compared to nitrophenol. 4,4 nitrophenol, the acidity is less. But 2,4-dinitrophenol acidity is more compared to the phenol and 3,5-dinitrophenol. But when you are increasing the number of nitro groups, that is acidity is very drastically increased. That is 0.4. Very strong acid. So we'll see some examples here, solve the acidities of different phenols, para-hydroxybenzaldehyde and meta-hydroxybenzaldehyde. If you see, para-hydroxybenzaldehyde is more strong acid than that of meta, because para-hydroxy, the involvement of delocalization will be involved into the benzaldehyde group, aldehyde group, whereas in meta-benzaldehyde, the delocalization is not into the benzaldehyde group, the aldehyde group. So para-hydroxybenzaldehyde is more strong acid than that of beta-hydroxybenzaldehyde. When you compare para-cyano, phenol and phenol, para-cyano group is electron withdrawing group, so the acidity is more for para-cyano group phenol than that of phenol. It is having a pK value of approximately 7, and the pK value of phenol is 10. We see para 2,4,6 trinitrophenol and 2,4,6 trimethylphenyl. Methyl group is electron donating group. The nitro group is electron withdrawing group. When you see drastically the acidity increases in para-nitrophenol, very, very strong acid, and trimethyl phenol, it is less acidic in nature. It is less acidic than that of phenol. So it is, we have discussed about the acidity of phenol and the effect of electron withdrawing group on phenol, effect of electron donating group on phenol, and relative strength of phenols. And we have referred the ball and ball, Merchant Boyd and IL-phenar for preparing these slides. Thank you. And next class, we will discuss about the basicity of amines and effect of substituents on basicity of amines. Thank you.